In honor of the nationality of our first speaker, we'll try to keep on time today. Let me also say we're trying to encourage our policy of keeping if you're on your laptops, please gravitate toward the back of the room, and we want to encourage you not to be on your laptops. Just take some time, enjoy the conference, be here. So I want to. It's a great pleasure to introduce our first speaker. Professor Billard is from Switzerland. She grew up in the Lausanne area. She went to EPFL for her undergrad degree in physics and actually worked at CERN, particle physics, the accelerator in Geneva. Then she moved to, she was given an offer at MIT to continue studying, and she moved instead to Edinburgh in Scotland, and there she discovered artificial intelligence, and she went on to study learning. And she was very early adopter and a pioneer in robot learning, working on connectionist models back in the last century, basically in the 90s. Then she moved to USC and University of Southern California in Los Angeles. She worked there for several years, and before moving back to EPFL, and where she continues to be a professor, leading a large research group in robot learning. Again, she's really established this area long before deep learning was a thing. And she is now, I'm happy to say, she will be she's the president-elect of the IEEE Robotics and Automation Society. So please welcome Aude Billard.
Thank you very much, Ken, for the very kind introduction. Good morning, everybody. It's early for many of us, or for some of us from Europe, it's fairly late. So I want to thank first Karen, Ken for the kind invitation, and Dana, also Minas for wonderful organization of the conference. I really enjoy that. I want to apologize to those of you who know already quite some of the work that we've done, because I'm going to start with things that you have seen before, and then we're going to move on the more recent research that we've done. So I'll start with things that probably many of you have seen before. We looked at how to catch a flying object, and it was particularly challenging because you have only a few milliseconds to compute a trajectory. It's particularly difficult when you're trying to catch an object like this one, which is half filled with liquid, because dynamics cannot be written explicitly. And so you have to use different techniques, among which we use machine learning. Now, the real challenge, and that's what I want to focus on here, are the following. When you want to compute a pass, you have really milliseconds in many cases, and you want to be able to plan really fast. So when we throw an object to the person, first of all, the dynamics is highly nonlinear, so you need to have a very accurate model of these dynamics. But even if you do have that, your real problem is that the time of flight is 0.4 seconds. In a robot, we always think of robot being fast, but they're actually very slow. So it's a little bit like the tennis player. If you want to catch this thing, you have to start moving right away. You have to start running to where you think the thing is going to land. And so to do that, you need to have an estimate. And if you have an estimate, you have an estimate of where it's going to land, and you want to go there, and you're going to compute a path. So always well, you'll think, okay, I have an estimate. It's fairly accurate. I have an estimate of the path I need to follow. But the reality is the following. As you go with your estimate, you have a real measurement. You keep tracking this in milliseconds, and then you see that it's not going to land where you hoped it will land. And so you have to adapt, and you have to really very quickly recompute a new path. And that's going to be the bulk of what I want to say today. Now, the problem of computing a real path is that you have no time to do so. You cannot run optimal control, even if you know that it's going to be done in finite time. Sometimes you don't even know what finite time exactly means. So the ideal is to have a model of all the feasible trajectory. And in my lab, we've thought about feasibility more than optimality for many years, where when you know what is feasible, anything will do, because anything is feasible. So you'll pick the first trajectory you can. And the best is, if you don't have to compute ahead, is when you have a closed form expression, analytical. So you don't have to do optimization. It doesn't matter if optimization is, again, finite time. If you don't have to optimize, that's much better. So how do we do that? And I'm going to do a quick wrap up of the approach that we followed for several years. So assume that we have a workspace, and I'll come back to the idea of how do we have a closed form representation of the workspace. But for now, let's assume we have some workspace, and we know that the object is going to travel and at some point land into the workspace. So what we want is to have a representation of this feasibility path. And the way that we approached that was to say, well, we do have a closed form solution of this feasibility space. So I remove now the representation of the workspace, and we just look at the feasibility space. We thought of it as saying, oh, we're going to go with differential equation. That's probably my background in physics, but in physics, you always use differential equation to explain any of the phenomenon. And you often have characteristics for this differential equation. So just a first order differential equation can give you a flow. And if it's time invariant, then gives you a flow of velocity, which we see here. And if we do have that in closed form, if we have this functional f in closed form, then we have an infinite number of those paths. And we just have to follow f. We don't have to plan ahead, especially if f has some guarantee. And here is a theoretical guarantee. So the one that we use mostly is this one, is to say that at the limit, it always goes to a single fixed point. So you have a differential equation, and when it vanishes only at one point. And what does it mean if it vanishes? It means that the velocity becomes zero, so you actually stop where you want to catch the object. Now, the big problem, of course, is what if f? If you do have f, then everything is fine. If you don't have it, then you can learn it. And we've done quite a lot of work on learning that from demonstration. So typically, you can get some demonstration like this. These are your sample. And from those samples, then you can build a probabilistic model, which we did as a mixture of Gauss function at the time. And then we could compute an explicit estimate, which is taking the expectation of the conditional of the joint model. In other words, we're asking what is the most likely velocity for the current state, and then we take the expectation, and it turns out it's a closed form solution, which depends on many different parameters, but all these parameters depends on the Gauss function. And we could show that to guarantee stability. If we use Lyapunov, which is one way of measuring that the energy decreases, then we could formulate that into an optimization problem, which is maximizing likelihood under stability constraint. And so it will give you different constraints, such as stability at the target, so ensure that there is only one vanishing point, and then that the energy decreases. So this was the background. And now I'd like to move to more some of the more recent work. Now, just to close, so what happens once you have this closed form solution is that you have your estimate, you want to go there, you have your estimate of where it lands. You always track whatever you want to get to as the origin of your system, which is just a transfer. And there again, if you remember your first class of physics, this is really always, if you put the origin of the system on a moving frame of reference, then you move with a frame of reference. And so it's an easy trick, and you can do that not just with the origin, but also with the frame of reference so that you rotate with it. So if we do have that, then as the rhythm measurement changes, then the origin of our system changes, and naturally we have a new path. And we don't have to compute this explicitly. It's done in closed form. Next, what we did was to don't have only one single fixed point, because that's very limiting, was to have multiple fixed points. This is called a multi-attractor system. And that's more difficult because one fixed point, that means, you just have this single one, and all the rest, you can use Lyapunov and the energy will decrease everywhere. If you have multiple of them, then you have to explain in which area of the state space is one fixed point valid, in which another point is valid. So let me give you an example of where it's useful in robotics. And if you want to catch this object falling, and you want to catch it either at the neck or at the top, depending on which falls, for just a tiny differences, it's going to be, you're going to have a different, let's say, attractor. Here, it's better to catch it not at the neck, but at the top of the object. But if it slightly falls differently, then you want to catch it at the neck. And you have even less time. You really have to move fast. So this is a multi-attractor system, because in joint space, these two attractors, they live elsewhere in Cartesian space as well. So you want to move across those two. This was, again, early work, so I'm going to go relatively quick here and then show you the most recent one that we have. We first thought of doing this as a classification and regression problem. I was teaching machine learning, and I observed, like most of you who teach machine learning, that support vector machine is very nice, because if you're familiar with it, it's a convex optimization that uses the exact same objective function for both the classification and the regression problem. Here, when we want to learn a classification problem, there are two regions for these two attractors. They live in two different parts of the space, but in each of these parts of the space, we want two dynamics that have two separate attractors and are stable. So learning the dynamics is a regression problem. Learning the part of the space is a classification problem. But you can formulate that as a single convex optimization where you rephrase the standard SVM with the constraint of the classification you leave on the left or right-hand side of the boundary, and then you add some additional constraint by taking the derivative of the flow that forces the thing to do regression. And so you can simply use the objective function of SVM and then combine the regressive and classification constraints, but applied to this particular case, which is following a dynamical system. And then you can add one more constraint, which is to reinforce the stability at the different attractors. So you can do that as a convex optimization. You retain the convexity of the original problem. And you can then learn and you do a multi-class classification. That means you classify one dynamics and then the other dynamics, and then you do an argmax to get the full dynamics. So that was one of the early applications that we did to be able to catch at runtime to choose if we were closing a tight fist or a large fist to catch. Right, so that's the end for the background. What we could do was to automatically partition space, as we see here, and learn different dynamics on those different partitions. But that was an exact partitioning of the space. And another problem is that it was a supervised learning problem. In other words, you had to know how many dynamics there were. You had to label your data points. In nature, there are many systems where it's not the case, where the dynamics are completely mingled. This is an example of the Duffin dynamics, for which the explicit equation is known. If you look at it, there is no clear partitioning of the space. The blue and the red trajectory both go to different attractors, but they're co-located in space. Tiny epsilon difference, and then poof, you end up in one attractor or the other. There are many examples where it can be useful also in robotics. So you don't have a clear partitioning of the space. You don't know how many dynamics there are. And in fact, if you were to observe the dynamics, you will think that there are more than two, because this other dynamics from the other side looks like it's following a very different path. So we thought that's a good starting point to think of this as an unsupervised learning problem. We like to be able to automatically infer how many dynamics exist, which shape we have for each of the dynamics, and where the attractors are located. So think of it as you have a data set which is composed of data points, all of which are unordered, unlabeled lists. You just put them in a very long vector, and these are your position and velocity, and they're in whatever dimension you want them to be. Each of those points, they represent different things that you sample in space, and you want to make out of this very unsampled long list how many dynamics there exist, if there exist many different dynamics, and whether they are stable at different places. So what the avenue we took was to first try to recover some of the underlying implicit information in these data points that are representative of the dynamics. And we started by thinking, well, they must be connected somewhere. So connectedness means graph. So let's build a graph, but a graph that is not very knowledgeable about the dynamics. So I can pick points in space, and then I can create a similarity measure to measure across all those points. Again, it's an unordered list. Compute a metric of similarity across those points. Then I can compute a graph by saying every single node that are close according to the metric will be connected. It's a binary graph. It's 1 if they're connected, 0 if not. Okay. Now the trick is the metric. You need to find a metric which embeds implicitly the information you're trying to extract, which is this notion of dynamics. For that, we propose a velocity kernel. So essentially, it's a kernel that will measure something that we are all familiar with, which is this notion of locality. It's the exponential decreasing function, the RBF function. So if I have 2 points that are far from each other, then this value is very large. So the exponential decreasing function is very small. And then if they're very close, then it's becoming very big. Now, another thing that we need to get the dynamics is to know that, that these 2 points are not just connected in space, because like I said before, we have points that can be close to one another, yet they're sending you into 2 different dynamics, 2 different attractors. So we're looking at another thing, which is this notion of directionality and continuity. And you can do that across all the data points that you have stored, and you're gonna look at whether the velocity vector are aligned or not. So if they are collinear, then it's good, and your metric is gonna be maximal. If they are not, then your metric is gonna be minimal. So when we do that, if we compare with the RBF kernel, and we take all the data points, here you see a graph of 2 different dynamics. We have the blue one and the red one. On the right-hand side, you have the gram matrix. If you use traditional RBF kernel, which only looks at locality, then it's clear that all the points in the middle are going to be connected. And that's what you're seeing, is that in your matrix of the gram matrix, it's not fully diagonal. It's going to have a lot of off-diagonal elements. We'd like to get rid of those off-diagonal elements. If we do use the velocity augmented kernel, which forces the system to put to 0 every single data point that do not have velocity that are collinear, then we can clear the space and be quasi-diagonal. We can do that even very, very complex dynamics, such as crossing dynamics as here, where we can get rid of those outer points and then diagonalize our gram matrix. Now, why is it interesting to diagonalize a gram matrix? I talked about graph, and graph don't use gram matrix, but the graphs are usually another matrix, which is called the Laplace, the Laplacian, or the Laplace graphic, the Laplace matrix. So I'm going to be a little technical, and then we'll see more robots. If you think of the Laplacian embedding of classically graph, what we usually do is that we put everything into a matrix, which is the Laplacian. So we go with this velocity kernel, the adjacency, we create the adjacency matrix for all the points that are connected and those that are not connected, and then we build the graph Laplacian. The graph Laplacian has a lot of very nice property, but one of which is that you can decompose it. You can do an eigendecomposition. So if we do an eigendecomposition, that means we have eigenvalues and we have eigenvectors. There are lots of very nice properties that you can exploit from those. One that has been used a lot in machine learning that you probably know under spectral clustering is the fact that if you look at the multiplicity of the eigenvalue 0, so the Laplacian always has the first eigenvectors with eigenvalue 0, but sometimes you have a multiplicity, and you do have that when the graph is disconnected. In spectral clustering, we use this when it's approximatively 0. So this is already known, and this is a nice way that you can recover the number of dynamics. You have this for free. You've created a graph, you've created this with this nice kernel, and then you get the number of dynamics. Just from these results, there is nothing very new in there. But then we looked at the eigenvectors of this, and it turns out that the eigenvectors are extremely interesting. If you look at the eigenvectors of this Laplacian, what you can prove is that they actually decompose into k set of eigenvectors, and among those, there exists always, if you have k dynamics, there exists always at least a pair of eigenvectors that have this property where 2 of the eigenvalues are equal, and also they're very small. And the funny thing is that it turns out that these eigenvectors have properties that follow Chebyshev polynomials. In other words, the entries of the eigenvectors are monotonic. So this sounds like very complex. What does that mean, that they are monotonic? Essentially, what it means is that once you project onto those eigenvectors, your dynamic suddenly is linear because it's monotonic. The monotonicity grows with the same eigenvalue, so they grow with the same rate, so it's linear. In other words, you went from having a very complex data set where you did not know how many dynamics you had. You discovered the number of dynamics using this notion of multiplicity of the eigenvalue, and then you discover eigenvectors immediately just from the graph Laplacian, and then you discover latent space plural. You have as many as you do have dynamics in which each of the dynamics are linear. I thought that was cool. We could prove that it was true for 2 eigenvectors. It turns out that we could also show that more recently, that it's actually true for, if you have a dimension of D, it's true for D-1 eigenvectors, which allows you to completely reconstruct this. It's not exactly linear, it's quasi-linear, and the quasi-linearity decreases, it becomes linear with O to the 1 over n squared, where n is the number of points. So the more points you have, the more linear you are. And so that's quite nice. So I'll just show you a couple of examples. So if you have an original dynamics like this, where you see this is only one dynamics, and we've extracted the dynamics with the clustering, what you can look at are the eigenvalues, and the eigenvalues show to you that there are 3 in this case that have exactly the same value. So they have the same eigenvalues. So there exist 3 eigenvectors that are monotonic. And you can do a 2D latent projection or a 3D latent projection where your system is linear. So you go from nonlinear to linear. Okay, D-1. So we went for four paths, and then we land into 3 dimensions. Here are examples with the pendulum equation or Duffing equation. They're completely mingled. We can flatten them. Again, we split that. So when you get 3 different trajectories in red and 3 in blue, then you end up with eigenvectors that represent these 3 dynamics, and all of which are linear. So the red one are for the red dynamics, blue one for the blue dynamics. The interesting part also is because the eigenvectors are naturally orthogonal, then when you split your dynamics, you split them into different spaces. So you can control these dynamics separately. Naturally, you just project yourself into one, and in fact, the other dynamics project onto 0 on the origin, so it doesn't act. How can we reconstruct the original dynamics? Of course, you project into the latent space. It's linear, you can control easily, but then you have to project yourself back. One can use any diffeomorphism at your disposal. We used some that have been published recently. And you can see here the type of reconstruction. We also showed that when we use this eigen projection, the Laplacian eigen projection, then because it does not require to invert the Jacobian as it was used to, then we will gain time. So we'll have half the training time. And we've just started looking at how to control robots to do these things. And this is just ongoing work. It's the first example, for instance, to do a very nonlinear dynamic, such as a spiral, and then being able to flatten it and to control from that. If I still have time, I'd like to shift a little bit topic now and to move to the second part. So I said what we want is to have something that is closed form, very retrievable in real time. And I started by saying we're going to use dynamical system for this, and we're going to have some representation of the feasibility space. Now, I'd like to talk a little bit about how we can get this model of feasibility space in real time when we're doing reactive obstacle avoidance, especially when we do it in high dimension. So it's a different topic from the previous one. So when is it useful to be able to react very quickly? It's typically when you're moving with a robot like this one in a dense crowd. Why is it difficult? Because a crowd, like we've seen here at night in a Christmas market, it's very unordered. It moves in all possible directions. And so you need to avoid pedestrian, and you can hardly predict what their behavior is going to be. So you have milliseconds. You also want to react very quickly because often in pedestrian area, then you have children and of course, or elderly, and you have people you need to really pay particular attention to. So dynamical system control are, again, very good for this because they give you naturally closed form solution for obstacle avoidance. This is not very novel. We're here following up on work that's been done by Slotin and Kodicek already about 15 years ago. But we extended that, and I'll show a couple of examples how we did that. So again, if we go back to our original representation, we have a dynamical system with asymptotic stability to some attractor. I can control a wheelchair like this. It goes in straight line. In this case, a linear system. And if it's, for instance, slides, then again, I can recompute immediately the path. Now, this can be used with obstacle avoidance in a simple way. If you do have obstacles here, you can represent them in your flow, and you can modulate your flow by a multiplication term. You multiply your original dynamics. And now you have to pay attention, how do I multiply that? So we're going to talk a little bit about eigenvalue and eigenvector again. If we want to multiply the flow in such a way that it doesn't go into certain area, then you need to make this area vanish. They need to become infeasible in your feasibility space. And you can do that with this M of X by creating a vanishing flow. So what we want is, of course, to preserve the stability of the attractor. So we want our M of X to retain stability. So for it to retain stability, in other words, our original dynamics must remain the original dynamics. So M of X must become identity close to the attractor in a ball around it. But close to the obstacle, we want this to disappear. So it should not be identity. On the contrary, it should be able to deflect the flow. So there are ways in which I can subtract like this. I can create holes in my dynamics, but my dynamics still flows. It's very much similar to what you have in fluid dynamics. Actually, it's completely inspired from fluid dynamics. So you want a flow to be deflected, and usually what you do is to deflect it along the tangent. So you need to compute the tangent to your space. And in order to compute your tangent, you need to have a representation of your obstacle. And that will be the rest of my talk. I'm going to talk about how we can learn, use machine learning to learn a very complex shape of this obstacle. But let's just keep now with this. Oh, I have 2 minutes left. Oh, I'm sorry. Okay. Is it? 30 minutes. So I have 13. Oh, boy. That's bad for my heart. All right, so I'll speed up a little bit. Okay, so again, we're back into this notion of moving frames. So M of X, what we did was to do an eigen composition. So as opposed to do an eigen decomposition as before, we can turn the problem around. You know, you can always create a matrix by doing a set of eigenvectors as you want, and then a set of eigenvalues. I'm going to go a little quicker. So one can compute a moving frame and then use this moving frame as the eigenvectors of this matrix, and then in such a way that you rotate. So you keep rotating with the moving frame. And then more than that, what you need is, of course, to make sure that your flow does not penetrate the obstacle. For this, you need to turn, and in order to turn, you need to make sure that any dynamics along the obstacle vanishes. So we can do that by computing a distance to the obstacle, it's closed form expression, modulate the speed, and then deflect. And what we can prove is that we do not penetrate the obstacle. We don't incur any local attractor except for one. There always exists one, but it's a unique spurious attractor, and so we can deflect that. More recently, we've expanded this by reusing something that Kodyshek had proposed, which was that you can enclose also the space. You can turn your boundary around. You can also force your system to live inside the space. And inside that space, you can have a dynamics which lives there. And also quite interesting, you can have a deforming space. So if you do have the envelope of your obstacle, and you know how this envelope changes, which is typically the case when you have pedestrians around, then you can always enclose your dynamics around this envelope and make sure that you don't expect. So we did, I'll go very quickly through that, but we did extensive assessment of that. Here it's the city market in Lausanne. We also went to the Christmas market, which is more complex because of the behavior of the crowds, which is very difficult, as I said, to predict. But not only that, it's also because it's night time. So the sensors are not very precise. You detect people very late. And most importantly, the density is really very high. So you have to constantly react to these different obstacles. But all of this you have in closed form. More recently, we showed that it was possible to also extend that to joint space and to be able to avoid obstacle with your different joints, as it is here. And for this, this is what I want to focus on, you need to have a distance in joint space. So to have a distance to obstacle, we need to have a function, gamma here, closed form expression. And if we do have that, then we can use it in so many different ways. We can enclose the space, we can compute explicitly if it's differentiable, we can compute the tangent, and we can always deflect the flow inside or outside. So here is where machine learning comes into the picture. How can we compute the distance function? So first we have to think of that when we do that in joint space, one problem is that it's high dimensional, it's non-convex, unlike what I had before with spheres and ellipse. I cannot compute it explicitly, and it's highly dynamic. So the very early work that we did, and that was done by Nadia Figueroa, who is here in the front row with other people in the lab, was to say, which time that I have a joint that moves, if I have two workspace of two robot arms with one another, and one moves, then the space for the other grows or decreases. If the first one moves away from the first arm, then the workspace grows. Conversely, if it moves towards me here, then my workspace decreases, and there are regions that are impossible. Now, all of this is known, all of this joint space is known, but it's very complex, so we can learn it. And one possibility to learn it is to sample in these high degrees of freedom space, to sample all possible regions in joint space that are collided and not collided. So you get lots of points. It's a classification problem, binary. It's very unbalanced because there are much fewer collided configuration than non-collided one. But you can rebalance this unbalanced thing, and then you can compute this. You have collided, non-collided configuration. You can use, what we did first was use a super vector classification that gives you nice things, such as that you have, explicitly with support vector machine that outside the boundary, you're either negative or positive, and you're exactly one at the boundary, and then you can use this as a gradient. And this could be formulated as a QP problem, so which was solvable in real time. And this was a very nice example of how this could be used at runtime. The two robots are tracking the attractors, which are the two hands of Sina Mirazavi here. And at the same time, they're avoiding each other at runtime. And of course, there is no time for planning, right? Because the person is just moving the arm left and right. Both are tracking this attractor, but they have to avoid the, each other and not collide with this person. More recently, we looked at how we could extend this in even higher dimensional space, which is this one, when we want to use the full degree of freedom of a humanoid robot, like this one. I always think that we have these beautiful humanoid robots, but we usually don't use the full number of degrees of freedom. And what I like is that they can crouch down and pick up objects. If you go with standard inverse kinematics, what happens often is that you're going to hit yourself. You're going to hit the joint. But again, all those joints, all these kinematics are known, so you can learn that. You have the kinematic, you can learn that offline. We compared what was the performance. In this case, we moved for neural networks, which were more performance in terms of the evaluation time after learning, of course, not during learning. And then we can use it at runtime, again, with a QP solver, same framework as before. And that's what you present. So pay attention, the red area represent the constraint that is active. Because it's high dimensional, it's very difficult to see, so we can only plot 2 by 2. When the constraint is inactive, it's blue. As the arm move with respect to one another, then clearly the constraints move, and that's what you're observing here. And so you have to find a path which is free of constraints, so you move away from the boundary at all time. Of course, here it's in 2D, but think of it as in high dimension. What is really nice is when you look at the result. So on the left-hand side, you have the self-collision model, which is going straight, linear. On the right-hand side, you see what is quite natural. You go down and then up, you lift yourself again. You put your butt up, basically, to give yourself more freedom, but still retaining the stability. Very, very nice example of application of this. I particularly like the one on the right-hand side, where it really uses all the degrees of freedom, all the workspace of the robot to pick up the box on the right-hand side. It's a little painful. It looks like the back is hurting for the robot. It's because it's stretching a little bit its joint. By the way, this is the iCub robot, and beautiful work done at IIT. Lastly, if Ken allows me, one thing that I'm absolutely passionate about is fine manipulation. So it's also same problem. We think a high degree of freedom in terms of humanoid robots, but our hands are also high degrees of freedom, and they collide with each other all the time, especially if you manipulate objects. I've seen too many examples in robotics where we pick up objects with only a 2-finger tip, as if we were disgusted by it. And I never do that. I always hold lots of things in my fingers. And so I so much wanted to see that. So recently, we've had a very nice piece of work done by Kenpo Yao in my group to be able to pick up and hold various objects within the hands to really use, again, all these degrees of freedom. And I'll show you a first video where you can really, once you have all this configuration, then you can put the object inside the hands and you can have the robot holding that. Now, this is completely pre-coded, handcrafted. The motion of the finger are pre-coded in such a way that they do not intersect with each other, and you can hold the objects nicely. And then I'll explain to you in a second why this is a problem. So yeah, this is just to show that it's quite reactive, and then we can grab the fourth object. So all of those are stable grip, and you can hold many different objects. But the problem, as you can see, is to compute a feasible path, which doesn't fall. So I thought of Ken, who said that we have to show our dirty laundry. So here we go. So when you hold an object, what often happens in reality is this. You hold it and then it slips, or what happened here is actually it got hit slightly by one of the finger when you were trying to grasp it. Now, this is dirty laundry, but that moved us to think about, again, how can we learn all this collision space so we can sample, same way as what we've done for the two arm, what we've done for the humanoid. You can sample in joint space of the hands. And once you have this, then you can compute at runtime. Here, the robot wants to close fist, but needs to avoid this particular object. You can compute at runtime avoidance of both an external object as well as your own finger until you manage to close the fist. This notion of obstacle avoidance can be turned around. You can avoid obstacle. Here we'll see again the same plot as I showed before, where you have the boundary and that keeps moving for only two fingers. We cannot see it in many dimensions. At the beginning, the path that you see illustrated here needs to avoid the obstacle to come and pick again the object, but then it needs to close on the obstacle. So you can turn this boundary always either by deflecting the flow away or bringing the flow towards it. And that's the nice thing about having a closed form expression of the boundary differentiable. So this is in simulation, and I'll close with having this in a real robot. So this is example where it was failing earlier on. Once you do have the obstacle avoidance methods, then you can compute explicitly this avoidance, go around it, and then eventually close. So with this, I really want to thank all the group, in particular Lucas, Mikhail, Xiao, Bernardo, and Aradhana for all the wonderful work that they've done, which I presented here, and I thank you for your attention.
Any questions?
Great points, and I love how you frame this in the context of classification. I'm curious about if you could say a little more about noise in these models, because the noise is implicit, right? And your samples are noisy. So I'm just curious, how do you explicitly treat that as noise parameters, or how much noise do you actually see, or does the noise sort of fall out of the model?
Yeah, so indeed, I mean, for any of those models, first of all, we're in simulation, we assume we have the explicit kinematics. And it's as accurate as it can be, which means it's not very accurate, especially because the kinematic chain usually does not give you, well, the kinematic chain will not give you the envelope of the volume of the robot. So we have to interpolate the volume. And the volume, the best way to do so is often to do it with set of spheres or set of ellipsoid, which will always be approximation. So frankly, the only way that we treat it is a traditional way, is to create a boundary. So when you do use super-vector machine, for instance, by construction, the boundary gives you a margin, and this margin, you can actually compute it as a distance in joint space or wherever it is, and then you can embed a notion, but you need to have a notion of how inaccurate you were about your boundary. And then we choose something that is essentially very conservative. So the result is that we lose a lot of free space. So it's a traditional classification problem where you will force the system to, it's a tumor versus no tumor. So you want a collided model to really yield almost 100% correct classification, and then the non-collided one can be wrong at some point, and then yeah, you lose some free space. Well, one possibility would be to relearn that, which we haven't done. That means that as you do incur in real time collision, to add this as a more data point, and in support vector machine framework, it's fairly easy to add this as one more support vector. In the neural network framework, it's a little bit more difficult. You're obliged to retrain the neural network. So there are pros and cons to the two approaches.
I had a question regarding the notion of stability you were talking about earlier.
Can you speak louder?
Sorry. I had a question regarding the notion of stability you were talking about at the beginning. You meant Sorry. With the notion of stability you were talking about at the beginning, where ensuring that the dynamics you have a Lyapunov exponent less than 0. This was for machine learned dynamics, you said, right? Or were those given dynamics?
So I can barely hear you, but I think your question is when did we use Lyapunov as a stability constraint?
Well, no. What I'm asking is if you're machine learning the dynamics, then how do you how do you ensure that the Lyapunov exponent less than 0 constraint is satisfied? Because in my experience, it's often quite difficult to make sure that the Lyapunov exponent is less than 0 on machine learned models of dynamics.
Right. So I see where you're coming from. In our case, it's a little different. We construct the model itself in such a way that it guarantees a Lyapunov constraint. It's the other way around. So you can, the very first work that I presented when we put Gauss function, each of those are covariance matrices that live in X and X dots. And you can study, again, you have to study the matrices themselves. And you can show that those matrices have properties such that an associated Lyapunov function exists that keeps decreasing. So basically, when you construct your optimization problem, you say, I'm looking for covariance matrices such that they yield this property. And then by construction, you do have that. Now, what happens is sometimes it's a little too conservative. So a lot of other work that we've done, including something that Nadia did, was to relax some of those constraints, not to be Lyapunov stable only, or to be P stable, or to be able also, that's the work we've done a lot with Jean-Jacques Slotine, was to use contraction theory to relax the constraints of being purely Lyapunov to stabilize. But the way that we approach the problem is the other way around, is to say, oh, I want to have this property. So I write my equation in such a way that by construction of this equation, it will have this property. I go back to my data, and then now I try to find a set of those functions that are as close as possible to the data. But my priority is to satisfy the constraints.
Okay,
from
thank you.
Hi, very interesting talk. I noticed that all the system described here are only subject to, let's say, ordinary differential equation. They're all very smooth. But for some robotic tasks, such as locomotion and contact reach manipulation, there could be algebraic constraint imposed onto those differential equations. Do you have any comments on how we can extend the methods here to the case with algebraic constraints?
Yeah, thank you for the question. So I didn't show that. We have extended extensively, actually. I should just say that we've published all of this work in a book, and lots of this work is also done at the end. I'm actually also teaching a class. You can have access of all the material, and we have extended this for force control. So we can control in force, we can control in differential equation, second order. And I tend to politely disagree with the idea that we do have discrete system and continuous system. We have shown that we can pick up very quickly objects. That means going from fluid motion to contact and then throw the object, for instance. It's work that I haven't shown, but if you go on our website, you'll see that we have plenty of examples like this, which traditionally you would think as discrete task, which is very similar to locomotion, where you hit and then you have contact, no contact, etc. But you can, I do believe that it's possible to control this with differential equation, because all of this is continuous. It's a transition across continuous systems. You do transition, but you do transition also in a smooth manner. And there is always the observer viewpoint. At a macro level, when you're far, it looks like it is continuous. But you know that if you look at it very closely and you're scaling down the time, then everything is continuous. The contact is going to be continuous. Slowly, you're going to have a new input, and then you will react to that. So we've extended that for admittance control, which means you have an external disturbances, for instance, which of course is there or isn't there, but you can still treat this as a continuous model. So we can discuss it more, but I tend to disagree with this view that we have discontinuous model versus continuous model. I think it's possible to have a continuous model all the time.
Okay, thanks. So my main takeaway from your reply would be that we can using model A as a continuous problem and handle the content naturally using the compliance or compliance of the robots. Am I correct to say that?
There is a terrible acoustic here. I can barely hear what you're saying.
Sorry.
But I suggest we discuss it at the break.
Okay, thanks.
Thanks. There was another question. Just April.
One last question.
Yeah, so really interesting perspective. And so I have a question regarding this obstacle avoidance and this kind of approach. So traditionally we had this vector field approach, and it had often the problem that you had sort of dead ends, or you would sort of go into a place where you wouldn't get stuck, right? And now in this tangent space approach that you have, it seems to go away, but I'm wondering, is there still a configuration of obstacles or so where you could get stuck, right? Because
it's not potential field. So the potential field approach did have the problem that you mentioned. So first of all, it had lots of local optima, and so you could get stuck and stop. At the same time as Osama Khatib developed this, there were also alternatives that came from fluid dynamics, which was proposed by, like I said, by Jean-Jacques Saltine as well as Kodicek. This is a work that we follow from. In this work, you can prove that there are no spurious attractor except for one single line. So you don't have this problem anymore.
yeah, so it's sync free essentially, except that so target. Yeah, pretty
yeah, it's free of spurious attractor. Having said that, it's true as long as you have certain type of obstacles. So they cannot be arbitrarily concave. They will have had to be star-shaped concave, but currently in the lab, we do have a solution that could be arbitrarily concave using contraction theory. It hasn't been published yet, so this is ongoing work. So I think we will never be able to get rid entirely of any spurious attractor. There will always be at least one, perhaps more than one, as many as the dimension. But what wasn't possible with the potential field was to be able to spell out where the spurious attractors were. And so you will end up, being stuck into some spurious attractor. What we're trying to do now is to have an explicit list of those spurious attractor, so that then we can handle them in advance, knowing that this is a fixed point. It's usually an unstable fixed point, and so be able to avoid this or treat it separately, especially if there are a finite number of them.
Excellent. Okay, thank you so much.